Okay, so now we're going to talk about the other types of hydrocarbons that exist, which are alkenes and alkynes. Remember that alkanes consisted of all single bonds. Alkenes and alkynes will have double and triple bonds. That's where we're going here. Okay. Alkenes and alkynes are also widely found in nature. Ethene, which is a 2-carbon alkene, is actually the gas that's released by plants as they're ripening. So for example, bananas and tomatoes and everything like that, you may have heard like they ripen a little bit better if you keep them in a paper bag. That's because they're going to be releasing ethene gas, and that gas also promotes the ripening of those. So that's what we're going to be talking about, and in particular, again, nomenclature. All right, so by the end of this, we'll know how to name alkenes as well as alkynes. Okay, an alkene is a hydrocarbon that contains double bonds, whereas an alkyne is a hydrocarbon that contains triple bonds. Okay, they're no longer considered saturated. Saturated would mean that they're all single bonds, so these are no longer saturated. We call them unsaturated. And we'll actually talk a little bit about the reactions that these types of compounds undergo as well, which is different from alkanes. Alkanes, we only talked about combustion reactions. Alkenes are actually what we're going to focus on more. They also undergo what are called addition reactions. Okay, so here is an alkene, and again, you can see that what makes an alkene is this carbon-carbon double bond. Okay, so that's what this guy here is. Remember that a single bond represents the sharing of 2 electrons. A double bond means that there are 4 electrons being shared. And when we're doing our expanded structures, we represent those, actually, as well as our bond line structures, we represent those as just 2 lines. Okay? Remember we talked about how alkanes, that carbon has a tetrahedral configuration. For alkenes, because there's still 4 bonds, but one of them is a double bond, so there's sort of 1, 2, 3 bonding regions. The shape of that carbon is a trigonal planar. Okay, so remember, in an alkane, that carbon was shaped like a tetrahedral. In an alkene, those carbons are shaped in a trigonal planar geometry, which means that they all lie in the same plane and they're exactly 120 degrees apart. So if you sort of visualize this as a 3D molecule. An alkyne, what makes an alkyne is this triple bond. So a triple bond is the sharing of 6 electrons, and how we represent that in our expanded structures, our condensed structures, and our bond line structures are 3 lines. Okay. They also have a different geometry than an alkene and an alkane. Alkynes, this carbon atom is considered to have a linear geometry. That means that the angle between these two is exactly 180 degrees. Right, so they're arranged in a line. Okay, because of that, we actually change how we draw alkynes. Okay, so first of all, this question just asks us to identify whether these compounds are alkenes or alkynes. What do you guys think for A? We have a double bond here, so that makes this an alkene. What about the other one? Here we have a triple bond, so that makes this an alkyne. And notice that with our alkenes, we didn't really draw them any different than our alkanes. It's just that normal zigzag, and then there was like an extra bond thrown in here, something like that. Alkynes, you draw in that linear shape, right? So what do I mean by that? This is a carbon, this is a carbon, and this is a carbon, all in a straight line, okay? So something like this, where I say that this is a triple bond, zoom in. Something like this where I say that this is a triple bond, this is wrong. If I wanted to draw this same structure, I would have to draw, here's my triple bond, boom. Now I can start doing the zigzags. Okay, so everything on either side of this triple bond has to be in a straight line. Okay. The endings that we're going to use are different, and actually it's kind of nice because it's the same as the category itself. So for our alkane, we had ethane, right? That ane ending. For an alkene, if we have 2 carbons, that would be ethene. If we had 3 carbons, that would be propene. Okay, actually, let me color code a little bit differently. This ethylene here, this is again kind of a common name. Let's ignore that. All right, and then if we have our alkynes, we use the -ine ending. So here's our alkyne. If it's 2 carbons, it's ethyne. And if it's 3 carbons, it's propyne. And again, we're just gonna ignore that common name, acetylene. Okay, and also the other thing I wanna point out is the bond line structure and how that's now linear for the alkyne as opposed to the alkene or the alkane. Okay, but we keep those same prefixes, which tells you the number of carbons. We just change the ending. All right, so Iupac naming for each of these compounds here. Okay, let's actually see if it's still excellent. So actually our steps are the same. There is a little bit of a curveball that I'll explain here in a second, but these are our steps. And remember, we updated this one. Actually, let me just grab it. Cool. So step 1, find the parent chain. Same idea, longest contiguous set of carbons. For alkenes and alkynes, you just need to make sure that your parent chain contains that double or triple bond. Okay, so in this case, this will be my parent chain. Now we got a number, and remember, we learned this thing at the end of the last lecture, where we're gonna actually number it both ways and then decide. Okay, so which one of these 2 numbering schemes do we choose? Okay, so this is where it gets a little bit different for alkenes and alkynes as just for alkanes. We're going to prioritize making sure that that double bond or that triple bond has the lowest number. We're actually going to ignore all the other substituents when we're looking at the numbering scheme and focus just on that double bond. Which of these numbering schemes gives that double bond the lowest number? And in this case, it's going to be the red one here. We always, when we talk about the position of the double bond, we do it at the lower number carbon. So this double bond between carbons 2 and 3, we'd say it was at carbon 2. And it implies that it's between 2 and 3. If we said that it was at carbon 1, that would mean it was between carbons 1 and 2. Okay. So then we need to figure out, so our parent chain is going to be a pent, 5 carbons, a pentene, and we're going to number where that double bond is. So not only is our parent chain a pentene, it's a 2-pentene. Okay, so you have to include the number of where that double bond is. We have our substituent here, which is a methyl group. Again, we said that it was the red numbering scheme that was correct, so I'm going to get rid of this blue one here. So this is 4-methyl 2-pentene. That would be the name of that compound there. All right, I actually might be a good idea to pause and see if you can't name this next compound, given what we've already talked about. If you can't, that's okay, but it's a good idea to try to put into practice what we talked about. Okay, so find that parent chain. In this case, there are 6 carbons, and then I'm going to number 1, 2, 3, 4, 5, 6, and then I'm going to go the reverse direction. 1, 2, 3, 4, 5, 6. Which one of these numbering schemes is correct, the red or the blue? Again, it's all about putting that special bond. In this case, it's a triple bond. In the previous example, it was a double bond. We want to make sure that that is sitting at the lowest possible number. So in this case, it's actually going to be that blue numbering scheme that's correct. And so we actually don't even have any substituents to worry about. So in this case, we have a 2-hexyne. And remember that that -ine ending corresponds to the fact that we have a triple bond between carbons 2 and 3. Okay, so when it comes to naming alkenes and alkynes, it's really not that much different than naming our alkanes with our substituents, except we need to make sure that the parent chain contains that bond, whether it's double or triple. And we're going to number so that that special bond gets the lowest possible number. We're not actually going to consider where the other substituents are until after we've decided on our numbering scheme. Okay, so this is just going to walk you through that. What about when we have a cycloalkene? So let me actually get rid of this here. Okay, so now we have a cycloalkene, right? So that means that the double bond is within the ring. Similar to when we were doing our nomenclature before, we want to find our parent chain. Again, because it's a cycloalkene in this case, the ring is the parent chain. And now we have to number that parent chain. Notice that there is a substituent here, but just like before, we're going to make sure to number this such that that double bond has the lowest possible numbering scheme. So I'm actually going to start going 1, 2, 3, 4, 5, right? If I want that double bond to have the lowest possible numbering, that means it needs to be between carbons 1 and 2. And so in this case, the substituent turns out to be at carbon 3. So that's why this would be 3-methyl cyclopentene. And notice that I don't have to say 3-methyl 1-cyclopentene. I can just say 3-methyl cyclopentene because I'm always going to number my ring such that that double bond is between carbons 1 and 2. Okay, so everybody take a second and see if you can't name these compounds here, given what we just talked about. Okay, so first of all, here again we have this cyclic compound. My parent chain for a cyclic compound is always the ring itself. And then we're going to start numbering such that the double bond is between carbons 1 and 2. So this would be cyclohexene, right? Where it gets that ene because of the double bond. And we don't say, you know, you really, I don't know. It's not the greatest sin in the world if you said one cyclohexene, but again, we already know that that double bonds between carbons 1 and 2. So what about here? What's our parent chain? It's going to be the ring. How am I going to start numbering? I'm going to make sure that my double bonds are between carbons 1 and 2. So 1, 2, 3, 4, 5. Now, if you're kind of clever, you might be saying, well, why didn't you number it the other way around, right? Because I could actually start over here and go 1, 2, 3, 4, 5. So why is the red numbering scheme more correct than the blue? Both of those keep our double bonds between carbons 1 and 2. So once that's the same for both of them, then you can look at the other substituent. So in this case, because if I'm looking at this methyl group in particular, these two methyl groups rather, they're going to be either on carbon 3 in the red numbering scheme or carbon 5 in the blue numbering scheme. So that's why we're going to pick the red numbering scheme. Okay, we're going to name, so that means our parent chain is a cyclohexene. All right, and then we have our two substituents, both of which are methyl groups. When we have two methyl groups, how do we refer to that? That would be dimethyl. And we actually have to include the number of both of them, right? So this would be 3,3-dimethyl cyclopentene. Right? It's a very common mistake for students to make to just say 3-dimethyl cyclopentene. Well, it could be 3,4, it could be 3,5, it could be 3,3. Those are all different dimethyl cyclopentenes. So you have to include the location of both methyl groups. Okay.